Welcome to this Advanced Healthcare Network SQL project, where I'll be diving into a complex data set using SQL Server Management Studio. The data I'll be working with is mock data, but the strategies I'll demonstrate could be applied across large hospital networks to uncover critical insights that drive better patient care and operational efficiency. Throughout this project, I'll be cleaning the data, identifying and removing duplicate records, resolving data entry errors, and ensuring data integrity, all of which are essential steps when dealing with large-scale healthcare datasets. To begin, I'll start by exploring the dataset and creating backups to safeguard the original data. From there, I'll format key fields, detect and handle duplicate records, and implement advanced SQL techniques to correct inconsistencies. By the end of this project, we'll have a cleaner, more reliable dataset that can serve as a foundation for deep analytical insights. The analysis focuses on various aspects of hospital data, including patient visits, medical conditions, finance, doctor activity, and admission trends. Key questions explored include which hospital has the most visits? Which patients have the most hospital visits? What medical conditions does the network treat? What are the most common blood types among patients? What are the highest and lowest medical bills? And we'll even take a look at a unique case where a doctor works with a patient that has the exact same name as them. With all that being said, let's dive into the SQL process and see these techniques come to life. So, here is our table. I have it pulled up in Excel and you can access it in the video description below. It's off of Kaggle, and I wanted to thank the creators of this publicly available mock healthcare database. Please note that none of the information here is actual patient's information, as we do have HIPAA laws in the United States. That being said, the processes used on this mock dataset will provide a similar framework to conduct advanced analysis on real healthcare systems. Some of our analytical findings can be a little interesting too, because of the nature of the dataset. However, this project will lay the foundation to develop a data querying pipeline for a real hospital network. So if we go up here and highlight all of the rows and columns, double-clicking them, we'll be able to expand and get a larger view of the database. As you can see, there's this name column which has interesting casing in it that is not congruent throughout. We have age, gender, blood type, medical condition, date of admission, doctor, and a hospital column with a lot of different hospitals, which indicates that this is a hospital network, not just one or a few hospitals. We have insurance providers, billing amounts with these very long strings at the end of the numbers. We have room numbers, admission types, discharge date, medication, and test results. We're going to pull that table into Microsoft SQL Server Management Studio. I have a database set up that I've called Healthcare, and we can just perform a task on it and import the flat file. From there, we can go into the folder where I have the CSV stored. We'll click Next and notice that all of our columns are right here. On the next page, we have all of our data types. The names are going to be an nvarchar50, meaning that it's going to be a variable character field that allows for up to 50 characters. The age is going to be a tiny integer, which just means that no one can be above the age of 255, which I don't think we'll have any problem with. We also have date admissions, as well as our discharge dates, which, as you guessed it, are just dates. The billing amount is a float number, and the rest of these are correct. We don't have a primary key set up for this database just yet. However, we're going to create foreign and primary keys as we clean up our data for analysis. We'll create patient IDs as well as visit IDs. So as we go through, we'll just finish this on up, close it on out, and refresh the database. And we can see that new table right here. This is the SQL script we're going to be using. I've already written about 700 lines of code. It's in the video description down below on my GitHub. To start off with, we're just going to do this select all statement from our healthcare database.dbo and then that healthcare data set. This is going to pull all the rows and columns. So
As you can see, this should look very similar to that Excel spreadsheet we had a minute ago, where we have the name, age, gender, blood type going all the way down here. What I wanted to take a look at first was this name column because I noticed that the casing for it was not proper and it also didn't follow any particular format. So what we're going to do to start things off is update that casing to proper case. Proper casing is how names are normally written in the English language, where you have the first letter capitalized, followed by every other letter in the name being lowercase, and then you'll have that second name or even third name also capitalized just in that first letter. So for instance, with this example, Bobby Jackson right here, we want that first B to be capitalized and then just the J in Jackson to be capitalized. And we want all the rest of the letters lowercase. But as you can tell with all these names, they're just kind of all over the place and there's no particular formatting for it, which can make it difficult to read and also difficult to perform analysis on later. It might make our end users a little bit frustrated too because of that readability portion. This update is going to reset that name column by taking the first letter from each substring and then making it to an uppercase. And then it takes that second string as well as the length just of the whole value of the word and separate it out into a lower casing. This XML path, what it does is it modifies words and then combines them back into a single string. And we're going to be separating out all of the words with this string split where there's a space. As you can see, not all names just have two words in them as well. We have some that have Miss Natalie Gamble or Mrs. Jamie Camp, etc. For some data analysis, you might want to omit these titles. However, it's going to be okay for us to keep those. We just want to make sure that we're applying proper casing for our database for that readability and usability functioning. Once we apply this update, you can see that it's going to change all that casing. We're just going to pull the top 100 here, so that way we don't have to pull all of the data and just helps with query optimization. And you can see that it is all cleaned up now. We have Danny Smith, Andrea Watts, all just with those first letters capitalized and the rest lowercase. You can even see that with like Miss Natalie Gamble here. We're going to focus on deduplication. How we do that is by selecting all of the columns in the database, grouping by all of those columns, and then filtering it down to where that occurs more than one time, meaning that we're going to find that exact same result a second time in the database, or maybe even more times than just two. As you can see, we have an example right here, Abigail Young, and if we pull that record from the database, you can see that the name, age, gender, all the way down to test results are the exact same. And what we need to do is pull that record from the database and just keep one of them. We'll provide a backup and then use this common table expression, also known as a CTE, that includes a row number window function in it. And what this is doing is this is partitioning the groups and sorting them arbitrarily, which then allows us to flag duplicates by checking for rows where the row number is greater than 1. As you can see, the row number here, which is this new column, indicates that there are two instances where Abigail Young is in the database. Once we've tested this, we can use this much larger function and actually apply the update to the whole database. We're going to be checking for every instance where that row number is more than 1, and then we can see that the duplicates are gone. This query is going to filter down any instance where the row number is more than 1, meaning that we have a duplicate entry. And luckily, we have eliminated all of the duplicates. Some strange errors are still taking place. It looks like there are a significant amount of data entry errors where two separate inputs were made into the system. Now, when this happens, every column is the same except the ages are different. You can see this example when we look up the name Aaron Archer, where the name is the same, gender, blood type, medical condition, all the way down to test results. However, that age is different. Now, the likelihood that a billing amount with an insurance provider and a blood type with a medical condition on the same exact date of admission is going to happen is super statistically low. And so we want to make sure that we're able to find every instance where this happens and make a correction for it. We'll select all of the columns and take a look at any instance where there is a distinct age that is more than one, meaning that that similar issue might pop up like with Aaron Archer, where there's a distinct age of 47 and a distinct age of 49. As you can see, these age variations happen almost 5,000 times in our database. Taking a look at where this happens, we can notice that the differences aren't necessarily linear. The age differences aren't always just two. For instance, Aaron Archer has this age difference of 2 years, Aaron Carr has one, Aaron Dalton also has one, Aaron Davis has three. In fact, there are even a few instances of Aaron Davis, but we can see that this actually is an individual entry without a duplication error. But this second instance of Aaron Davis, which we can delineate by having its own unique blood type, is definitely a duplication error. For the sake of our project, let's say we went back to our data entry, administrative, or financial team and realized the reason that this double entry error is occurring is that during admission, patients' names are inputted twice accidentally sometimes. And so what we need to do is just go back in and delete any instance where that age is higher than the first instance. For example, with Aaron Archer, we're going to keep the age 47 and get rid of the entry where the age is 49. We'll back up the data and then pull all the records where this double entry error occurs. As you can see, it happens almost 5,000 times. And what we're going to do is perform this version of a self-join and delete all of the instances where the age is higher than the first instance of the age. Again, we're going to be getting rid of that version where the age is 49 for Aaron Archer and just leaving the instance where the age is 47. As you can see, when we check where any of those duplication errors occur, we have eliminated all of them, and we just have 0 rows now where there's a second instance where there's another age, and then one of them is less than the other one. As an overview, what we've done so far is clean up the names in our database, as well as just make sure that every instance that a patient visit happens in the database, we only see it one time, and there aren't data input errors. What this allows us to do is create a foreign key as a patient ID for each patient, even if they came to a hospital more than once. This can help us to filter and analyze the data later. In order to assign a unique patient ID, we need to find a unique instance when a patient's name, blood type, and age, plus or minus the date range of the whole database, occurs. The reason we account for this variance in age is because a patient might come in on a different year where they are a different age. For example, if a patient comes in the year 2020 and they are 20 years old, and then they come in the year 2022 and they're the age 22, we want to assume that that patient is still the same person, even though their age is marked different in the database. The first step is to calculate the date range of our database. I'm going to subtract the minimum year value from the maximum year value. This maximum is even going to be ceilinged just to make sure that we're casting as wide of a net as possible and not missing any values. That number is 5, and I'm going to even use 6 just to be extra safe. As always, we'll create the backup, then make our alterations. The patient ID column is added as an integer value by altering the table. Then we'll run the main query. With a common table expression and a row number window function, we assign a unique number for each instance of a name, blood type, and age. Then we'll perform this left join on the table to determine all of the matching names, blood types, and ages with a variance of plus or minus 6 years. The dense rank function towards the end makes sure that patient IDs can be assigned to patients that have visited a hospital more than once. When we run this, you'll see that a unique patient ID has been assigned to every row in the entire database. So this patient ID is over here. That's going to be assigned to the name here. Up next, we're going to take a look at this billing amount column. We have a lot of very long decimal places in this column, and we want to make sure that we're just rounding it out just to 2, because that's what's going to ultimately help us out best just for our financial needs. As always, we're going to provide that backup to our database, and then we're going to work through an update. We're using this convert decimal query, which is going to allow the whole number to be 10 digits long, and then have the decimal just 2 values out. As I run this and then take a look at the top 100 results, you'll see that all those values are just now down to 2 decimal places. One problem with this conversion is that if there is a 0 value in the hundredths part of the number, then it's not going to show that extra 0 because of the format of the number. So what we're going to do is just provide a quick alteration to the table and to the column, allowing it to place that second decimal value on that number. So you can see this now. This is going to round it out to 10 pennies or 10 cents, 80 cents, as opposed to just 0.8. It just helps us keep the uniformity with the numbers, and it improves the readability. So this is amazing. We have cleaned our data set, including deduplication, cleaning up that name column. This billing amount column now looks a lot cleaner. And we're just going to dive in and show how this deduplication process looks now that the data is cleaned. This query is going to pull any instance where a name appears more than once in the database. Again, if someone has the same name, but they are either vastly a different age, or if they have a different blood type, that's going to indicate that they're a different person, which is what this query should show when we run it. As you can see, we have a patient here named Aaron Harris. They were seen on February 3rd of 2020, and there was another Aaron Harris 3 years later who was age 29. So obviously this person should not be the same person, and our patient IDs are correct in that instance. We have patient ID 60 for this person, and then patient ID 61 for the next instance. We're going to pull the names Adam Williams and Amanda Johnson because they appear so many times. As you can see, there are different blood types and a large difference in ages just across that 5-year span that our whole data set runs over. And we have those unique patient IDs assigned to each individual person, indicating that these patient IDs were correctly assigned to different people. I'm going to add a visit ID column as well. This is going to look like a very similar process to our patient ID column, in which we are providing a row number in relationship to the date of admission for each visit that happens. We provide the backup, then update the table with that integer column, which we're going to call visit ID. Once we do that, we can run this prompt and then check the work. We know this is correct because the visit ID starts at 1 on the very first day of our whole database and then runs through every date afterwards in that sequential order. Now we have a name column, age, gender, blood type, medical condition, date of admission, doctor, hospital, insurance provider, billing amount, room number, admission type, discharge date, medication, test results, patient ID, and a visit ID column for our database. We've cleaned up that name column as well as the billing amount, and we've assigned the patient ID and visit ID accordingly. Because of that, we can now jump right on into our analysis and get some answers from this data. We'll start off answering some more basic questions about our data and then dive into some more heavier statistical analysis and just a deeper dive into what we can understand about this data set. As a reminder, this is a practice database, so we're not going to provide any real correlative effects between blood types, age, medical conditions, or any other piece of this database, but we are going to be able to provide the groundwork to be able to implement a system just like this into a real hospital setting. Hypothetically, an analytical strategy similar to this one could answer some of those questions that a hospital might be investigating. However, I very much encourage anyone to do a lot of their own research before just implementing a system exactly like this into their own setting. Our first investigative question is, which hospital has had the most number of visits? This is going to be a fairly simple select, count, and group by and order by query, where we see that LLC Smith has had 40 visits total. Again, being that this is a practice database over the course of 5 years, you would probably see a lot more visits at a hospital over the course of 5 years than just 40. However, again, we see that that one is at the top of this list. Something that hospitals are always looking at are readmittance rates. This query helps us see which patients have had to visit the hospital at least twice, and we can see that 7 patients have visited 3 times over that 5-year period. Up next, we're going to take a look at which medical conditions this hospital network treats. We do this by doing a select distinct query on that medical condition column, which just pulls each individual medical condition that is in the database, even if it occurs 10,000 times or 20,000 times. I just want to know which individual ones we see. And so what that query shows us is that we treat diabetes, cancer, arthritis, asthma, hypertension, and obesity. Hospitals operate off of a large influx and movement of money, and so it's very important to know where those bills are going. I'm curious what the highest single medical bill that any individual patient has, and we're just going to kind of pull the top 100 results. As you can see, this patient named Todd Carrillo has a bill of $52,764. And most of the other bills that a lot of these patients have are fairly similar to that. On the contrary, we're going to take a look at what the smallest medical bill that a patient has. When I first started running these queries, I noticed that some of the answers were actually negative, which might indicate that there was an overpayment issue or maybe double or triple dipping with certain insurances. And so I just wanted to take a look at the values that were above $0, knowing that I might need to report those negative values maybe to a financial team just to let them take a second look at them, just to make sure that those sheets get balanced out. When we run this query, we're going to do it in ascending order, unlike the descending order of the last one. We can see that Wendy Dillon owes $9.24, Tom Dillon owes $23.73, and so on, just kind of taking a look at the top 100 results. Outside of the maximum and minimum medical bills, I am curious about the average. When we pull this, we're going to cast it as a decimal value just to that two decimal places. Otherwise, we're going to end up with another answer that's just very long and a little less readable. We can see that that value is at $25,000, 561 and 41 cents. This next one I originally thought would just be kind of a fun one to practice, but might not have many practical uses. I was curious if there were any instances where the name of the patient was the same as the doctor. Once I ran this query, I noticed that there was a patient named Mary Miller who was seen by Dr. Mary Miller, and it got me thinking that there might actually be a case where you'd want to check for potential fraud, making sure that a doctor was not either prescribing themselves medications or assigning themselves specific treatment modalities that are not double checked by another doctor beforehand, which can be a legal issue in the United States. The name Michael Williams appeared 22 times in the database, and I wanted to just pull those records to see if there was anything unique about that number or about why that was. And after looking through it, honestly, I did not really see anything that stood out. However, that's totally fine because sometimes in research, and analysis. We just need to look into something and it might not pull back any results or anything substantial statistically, but it's good for us to check that just to make sure that our data is still accurate and clean, and that way we're looking into any trends that might be associated with this. In my mind, maybe there was just a lot of people in this town or that utilize this service that are named Michael Williams, but there's really nothing statistically significant about that. As I mentioned earlier, this is a database for a hospital network, and I was curious how many doctors work at more than just one of the hospitals. So we're going to count all of the instances as this alias of the doctor count from where we're doing a subquery. We're going to select the doctor from the database, grouping it by doctor, having a count more than one on a distinct hospital. So again, this is going to pull any instance where a doctor works at more than just one hospital. And we see that 5,856 of our doctors have worked at more than one hospital. We can see which doctors have had the most number of patient visits. We're going to pull the top 10 results here. And out of those 6 medical conditions that our hospital network treats, I'm curious how many times each one of those is treated. We can see starting from the top, we treat arthritis the most, and we treat asthma the least. Going into some time series analysis, I was curious which years had the most to least amount of visits from that time period 2019 to 2024. We can see those results here. 2020 had the highest number of visits, and then in 2024 we had that really low number of 3,434. Now, if we remember going back to our database, there might be a reason for that, being that we might not have all of the data from that year yet. So it might be important for us to reach out to our data entry team before we were to just report on this number, stating that from the whole year, we only had that many different visits. This 2019 number is pretty interesting though, because it is significantly lower than the other years. This might indicate that the hospital network was just coming online, or we might not have had a lot of data entry or just data collection around that time period. Either way, this is something to look into and try and see why that number was so much lower. In order to assist inventory management as well as just planning for the future and how we want to make sure that we're helping our patients the best, I was curious what the most prescribed medication for asthma was. Again, this is not a real number from a real use case scenario, but in this one, it would be Lipitor. Medical treatment and planning can look different by gender, so it's important to know that distribution. Distribution by admission type is extremely important for triage models, and so I wanted to take a look at the difference between urgent, emergency, and elective visits in this network. Emergency visits usually require the most amount of resources, and so I was curious what the distribution of medical conditions was where the admission type was emergency. And we can see that obesity was our highest one, arthritis, diabetes, cancer, asthma, all the way down to hypertension. Knowing what blood types you have in a medical network can help provide life-saving care to people in emergency situations. Being able to easily access these numbers through a dashboard or report will help with proper resource management. Understanding the distribution of insurance types that your patients have can help with resource allocation, financial risk management, contract negotiations, as well as improve service optimization for clients and staff throughout your whole network. The next question looks at the average bill amount by medical condition. Looking at this can help us understand which medical conditions we're charging for the most, which ones we're charging for the least, and how costs vary across different diagnoses. This insight can help hospitals assess pricing consistency, identify potential inefficiency in billing practices, and evaluate whether high cost conditions align with resource utilization. Additionally, understanding these trends can inform negotiations with insurers, optimize budgeting for medical departments, and highlight opportunities for cost reduction or process improvement. Analyzing this data also supports strategic decision making, such as expanding services for high revenue conditions or addressing affordability concerns for patients with lower cost treatments. We'll take a look at which hospitals have the highest total billing amounts, as well as the average length of stay in days for each medical condition. We'll use a date diff function for this query to determine the difference between their date of admission as well as the discharge date, taking an average of it. This being a model database, we're just seeing this 15 number across the board here. However, this function would work across a diverse set of real numbers. Next, we're going to take a look at the trend in hospital visits over time, specifically on a monthly basis. We use this format function to convert the date of admission into a year, month string format, which allows for grouping and ordering by month while preserving readability. As we query this information, we can also pull it into an Excel spreadsheet and create a very quick column chart, which shows that there's a dip in February of 2021 as well as February of 2022. Both of these instances I think are significant enough to bring up to a management team. Moving forward, we're going to take a look at which patients have had the highest total billing amounts across all visits. We group by their patient ID and then the name, because if we just grouped by the name, we would have an aggregate function of these Michael Smith names, which we looked at earlier. Again, there are 22 instances of Michael Smith in the database. However, we're just concerned about this patient 34171 and this total bill that he has of $105,000. We'll take a look at which doctors treat the most diverse set of medical conditions. When we run this query, we'll see that there are actually quite a few doctors that treat for all 6 conditions that our hospital network treats for. On the flip side, we should know which patients have been admitted for multiple medical conditions. We do this by using a having statement in the group by function where the distinct count of the medical condition that they have is more than one, meaning that they have more than one medical condition. We have 34 patients in our hospital network that we have treated for 6 multiple conditions. What I was curious was how often we are treating each one of those medical conditions where the patient that's coming in has been seen for all 6 medical conditions. Even though there are only 34 patients that have been in, sometimes they might be coming in more than once for a medical condition. And so I wanted to know which ones we're seeing the most. And as you can see, arthritis and diabetes we're treating for more so than asthma. When a patient is coming in with multiple conditions, it's known as comorbidity. Why it's important for a hospital network to track comorbid conditions is because we can improve patient care, optimize resource allocation, enhance predictive analysis, reduce costs and readmissions, as well as support public health and research. On an individual level, we're able to provide more personalized treatment, reduce the risk of complications across those multiple conditions, as well as provide better medication management, which hopefully can reduce to fewer hospital visits and readmissions. This increases the patient's chance of improved long-term outcomes, as well as allows the hospital network to provide a more efficient and coordinated care system. We're also going to take a look at the distribution of comorbid conditions when the number of medical conditions that a patient has is only 5. What this can show is how the severity and progression of certain diseases and conditions affect patients, as well as help us understand how we can best utilize our resources and provide the most effective treatment modalities possible. This query identifies patients who were readmitted to the hospital within 30 days of a previous admission. It first creates a temporary data set using a common table expression, again, that's that CTE, where each patient's admission date is paired with their next admission date using the lead function. Then it filters for cases where the time between admissions is 30 days or less, counts the number of readmissions per patient, and ranks them in a descending order. This helps hospitals analyze frequent readmissions and improve patient care strategies. For our last research question, we're going to take a look at the correlation between age and billing amount. This final query calculates the correlation coefficient between age and average billing amount, which helps determine whether there's a relationship between a patient's age and their hospital charges. First, it creates a CTE known as billing by age that groups patients by age and calculates the average billing amount, ensuring values are cast as floats to prevent errors. A second CTE that we're calling stats computes necessary statistical sums, including total counts, sum of individual values, sums of squared values, and sums of multiplied values. Finally, the main query applies the Pearson correlation formula, showing how strongly age and billing amounts are related. Because the correlation coefficient was negative 0.33, we're going to say there's a weak correlation between age and the billing amount that a patient gets. This could actually be a good thing, though, because it could mean that across the entire network, they're providing equal billing practices across all ages.
Thank you so much for following along with this Advanced Healthcare Network SQL project. We successfully cleaned and analyzed the data, which gave us a unique perspective of our database. We uncovered valuable insights that can help healthcare networks improve patient care, optimize operations, and make data-driven decisions. From identifying hospital and patient visit patterns to analyzing medical conditions, billing trends, and admission demographics, we explored a wide range of critical questions. We discovered which hospitals and doctors are the most active, which medical conditions are treated the most, and looked at unique cases like patients sharing names with their doctors. We also delved into financial insights such as average billing amounts and total billing by hospital, as well as admission trends and patient demographics that shed light on how healthcare services are utilized. The advanced investigations, such as analyzing patients with multiple conditions or exploring correlations between age and billing amounts, provided deeper insights into the complexities of healthcare data. These findings not only highlight the importance of data integrity and cleaning, but also demonstrate how SQL can be a powerful tool for uncovering actionable insights in large data sets. As we wrap up, remember that the techniques and strategies used in this project are applicable to real-world healthcare scenarios. Whether you're working with mock data or actual patient records, the principles of data cleaning, analysis, and exploration remain the same. By ensuring data accuracy and leveraging SQL's abilities, you can transform raw data into meaningful insights that drive better decision making and improve patient outcomes. Thank you so much for being a part of this journey. I'm David O'Brien. If you'd like to chat, leave a comment or connect with me on LinkedIn. As always, have an amazing day.